Welcome to this explainer. Okay, picture this. You're a junior design engineer, and you've just modeled a beautiful, perfectly routed copper bus bar in your 3D CAD software. It clears every single obstacle, the dimensions look absolutely pristine on your screen, and you confidently send that drawing straight to the shop floor. But, a few days later, the fabricator walks up to your desk holding a piece of copper that doesn't fit the switchgear panel at all. Sound familiar? Well, today, we're going to bridge that gap between your perfect digital CAD models and the physical, sometimes pretty unforgiving realities of busbar fabrication on the shop floor.
Here is our survival guide for today. We'll be hitting number 1, the cost of close enough, number 2, properties and mechanical limits, number 3, demystifying the K-factor, number 4, the bend allowance formula, and number 5, springback and shop reality. Let's get right into it.
All right, Section 1, the cost of close enough.
This really gets to the heart of our core challenge. Bus bars are rigid conductors. You know, if you're routing flexible cables and you're maybe a millimeter off, it's no big deal, right? You just nudge or reroute the cable to absorb that tiny error. But copper bus bars, they do not forgive. If your pre-bend blank length is wrong, you simply can't stretch it. That little mistake instantly becomes rework, extremely expensive scrap material, or honestly, worst of all, it turns into mechanical stress because an operator forced a poorly fitting joint together.
So the takeaway here is that dimensional discipline isn't just a nice to have, it's totally mandatory. We're not just trying to make things look neat on a drafting table, we actually have to maintain strict creepage, clearance, and assembly verification standards under IEC 61439. A bar that looks, close enough when it's sitting flat on the workbench might actually force the insulators completely out of tolerance once it's bolted in. True precision in your flat layout is the only way to guarantee a clean fit in the final assembly.
Moving right along to Section 2, properties and mechanical limits.
Okay, before you release the next drawing to the shop floor, I want you to ask yourself, what physically happens when your theoretical radius clashes with the actual machine tools? I know it's super tempting to just type in a tiny bend radius because, hey, it makes your 3D model look incredibly sharp and compact. But guess what? The heavy machinery and the actual laws of physics have the final say here.
When you look at the minimum radius requirements, you can see exactly what those physical limits are. If your radius is too tight for the specific temper of your copper, the outer face of that bend is going to craze or completely crack, and that drastically reduces the mechanical quality and the current carrying reliability of your bar. For soft annealed copper, sure, you can generally get away with an inside radius of half the material thickness, but look at hard-drawn copper. For that, you need a radius at least 1.5 times the thickness. The rule of thumb? Always match your required radius to the actual die set sitting out on your shop floor.
All right, Section 3, demystifying the K-factor.
So to really understand the K-factor, you first have to wrap your head around the neutral axis. When flat copper bends, the inside face of the curve physically compresses, right? And the outside face stretches. But right dead in the middle between them is this magical layer that simply changes direction without changing its length at all. And that, my friends, is the neutral axis.
Now here's where it gets really interesting. The K-factor is actually just the position of that neutral axis, expressed as a fraction of the material's thickness. And here is the kicker. It is not a fixed, universal constant. It shifts entirely based on two things, your copper's temper and your inside radius to thickness ratio. For soft copper, it can range from 0.33 on really tight bends all the way up to 0.50 on wide bends. Basically, a lower K-factor shortens your bend allowance, and a higher one increases it.
Which perfectly sets up Section 4, the bend allowance formula.
I know it looks like a lot of alphabet soup, but this standard bend allowance formula is literally your best friend. It calculates the exact length of material consumed as the copper wraps around that neutral axis arc we were just talking about. It's really just simple geometry. Pi over 180 converts your bend angle into radians. Then you just multiply that by your inside radius plus the K-factor times the thickness, boom. So, to calculate a proper 90-degree or offset bend, you just follow these exact steps. Step 1, calculate the bend allowance. Step 2, measure your straight legs. But listen up, because here is the absolute golden rule that trips up so many new engineers. You must always measure your straight legs to the tangent points of the bend. Never, ever to the bend center. Finally, step 3, just add the straight legs and the bend allowance together. That whole shebang gives you the exact flat, developed cutting length for the raw material.
And that brings us to our final section, springback and shop reality.
You know, you can do all the perfect math in the world, but you have to remember that copper has elasticity.
Springback is the elastic recovery that opens the bend up slightly after the heavy forming press releases its load. Basically, the copper literally fights back. Especially when you're dealing with hard-drawn copper and large radius bends, the material is going to relax and open up to a slightly larger angle the literal second the operator lets go.
To compensate for this elastic recovery, seasoned fabricators use what's called an overbend. They'll actually bend the copper slightly past your intended angle, usually somewhere between 1 and 4 degrees, depending entirely on the temper. Soft copper, it might only need 1 degree, but hard-drawn copper might need up to 4. The only way to know for absolutely sure is empirical humility. You have to fine-tune the exact angle with a sample piece of scrap copper before running the final production parts.
So, let's turn all this into an actionable checklist of daily habits that will actually connect your formula accuracy to real-world repeatability on the floor. First, mark your tangent lines. Second, verify the actual die radius on the machine before you release the drawing. Third, deburr your cut ends so you don't inadvertently create tiny crack starters. And lastly, this is a real game changer. For parts with more than 3 bends, build a simple cardboard template first. I'm serious. It exposes orientation mistakes in minutes instead of wasting tons of expensive copper.
At the end of the day, the absolute best engineering happens when theory shakes hands with shop practice. Empirical humility and genuine collaboration with the machine operator are what elevates you from a good drafter to a great design engineer. Your math will absolutely get the layout 99% there, but the operator's tooling and deep material knowledge is what closes that final gap. So, I want to leave you with this thought. The next time you finish a highly complex layout, are your theoretical CAD lines really ready to survive the physical realities of the press break? Thanks for joining me on this explainer, and I'll catch you next time.